Okay, page 323, number 15, looks like this. We have a situation, mass on a spring, we know the mass, we know the amplitude, or maximum displacement from equilibrium, and it swings back and forth, or springs back and forth, 2.2 times per second. So that's the frequency measured in hertz. Period of oscillation would be the reciprocal of that. Part A. The speed at equilibrium will be its maximum speed. So out here it has an instantaneous speed of 0. Right in here it has a maximum speed. Before we find that, we need to find the spring constant, which we can do from the equation for a period of oscillation. So 2 pi times root m over k. Solving that, rearranging for k, looks like this. So this is just sort of fun. You don't necessarily have to do that. You could just kind of plug in. But I always like using my algebra skills. Substitute, solve, notice the units for spring constant, Newton per meter. Then what we're doing is we are equating the potential energy out here to the kinetic energy here. So this doesn't always work. Okay, but in this situation it does. Oh, great, here come a bunch of kids. I'm going to pause. Okay, back again. Oh, great.
All MHS ski team members, please come to the office immediately. All MHS ski team members.
Alright, I have no idea where we were, but I think we're somewhere in here. The potential energy out here, potential energy out here will equal the kinetic energy at the equilibrium position. Well, right, that doesn't always work, but it does in this case. So, again, using algebra skills to rearrange an equation. Velocity is this, and plugging in and getting this. Now, if you look at the original question, we have two significant figures. So we should actually write this as 2.1 meters per second. Okay, for part B, it's 0.1 meters from equilibrium. So that means it's going to be either here or here. And it can be on the way out or the way in, and it's going to have the same velocity, which I know sounds a little weird. I didn't just say that. It's going to have the same speed, which I know sounds a little weird, but that's the way the world works. For example, if you throw a ball into the air, at this height, it's going to have the same speed. Yeah, it's moving up. Yeah, it's moving down, but same speed. Just opposite direction. So, we don't have to know that, but what we do is, so I set this up. Imagine this is equilibrium position. This is 0.1 meters away. This is 0.15 meters away. Out here, all the energy is potential. In here, all the energy is kinetic. Here, it's a mixture. So we're setting the maximum potential energy, which is actually the total mechanical energy. We're setting that equal to the potential plus kinetic right here. We know from the kinetic we're going to get the velocity. So over here we have kinetic here equals this minus this, meaning maximum potential minus the potential at 0.1. So here's maximum potential, here's minus potential at 0.1, and we kind of set the kinetic equal to the 1/2 mv squared, canceled out the 1/2s, rearranged this equation for v, plugged in, and got this. Significant figures would have us writing this as 1.5 meters per second. Okay, so if you just, and maybe you're noticing some eraser marks here. At first I just plugged in 0.1 instead of 0.15, and I got the wrong answer. So don't do that. What that would give you would be the speed speed at equilibrium if it were released from point 1. Okay. So moving on to part C, total energy. Well, yeah, that's kind of easy. We just did that. 1/2 kx squared, where x is the amplitude or maximum displacement. Know that the units would be in joules, and we would have something like that. Okay, so part D, this is the thing that I think students kind of have some trouble with. We're taking what we remember or don't remember from trig and applying it to AP Physics. Cool. So I don't know how you first learned this, but the, let's see, watch this, yeah, alright. So our sine and cosine graphs look something like this. Let's see, where this would be ym. This is our angular frequency, meaning every time this many seconds go by, every time this many seconds go by, this is going to end up being 2 pi, and so the graph of cosine will go through one complete oscillation. And 0.15 is the amplitude or maximum displacement. The question D said something to the effect of at t equals 0 it starts at maximum displacement, which is why I chose cosine. Okay, if the graph were offset, so something like this, it would mean we would have to include some crazy number in here, like this. That's called a phase shift, but we don't have one here, so let's not do it.